Welcome. Let me say something about relativity. I have to warm up for next week when we look at the classical theory of relativity, which is an application of Riemannian geometry. So when we look at these equations, especially the Riemann curvature tensor, and then the Regge tensor, the scalar curvature, and then the Einstein equations. So all of these can be implemented in a few lines of mathematics or a few lines of code. These few lines compute everything, compute the Einstein tensor of a general manifold if it is given by a parametrization. So if you have a parametrization, everything is very, very concrete. So there are two pillars of relativity. First of all, we have these partial differential equations, which are hard to solve. So this is a additionally given matter tensor, which it can be electromagnetic matter, it can be kind of a fluid type stress tensor, and this is also a two tensor here. And then we have an ordinary differential equation which gives the motion of the particles in that field. So these equations tell us what happens when you have the matter given, gives us the geometry, and these equations tell us if we have the geometry given, what happens with matter. Nobody tells you in this theory actually how this works together, because the matter actually also changes the tensor here. So there is an interaction between these two things, and already in a two-body problem that's just so hard that it's really, really ugly if you are doing this numerically. So there is no explicit solution of this system. It's not even part of that framework, right? Because you have here the particles are moving in the geometry, and the geometry is determined by so this should be part of a larger theory. So I want to there's a nice principle, nice variational principle, a Hilbert-Einstein action, which has been found essentially in the same time by Hilbert and Einstein. And then here is also an action principle, minimization problem of action or length, and that gives you the geodesics. Now you can ask, how does that work in the discrete? And in the discrete, this has been done by Regge 60 years ago. So Einstein, it's kind of just half time. Einstein started to think about this in 2001, so when he was in Schaffhausen, where I grew up, and so 60 years later came Regge with a calculus. So Regge around 1960, this is covered in chapter 42 of this book here. So actually this book is how I gain my strength, right? This is such a heavy gravitational book. It's 1,300 pages. But the funny thing is that, Hitchhiker's Guide of Galaxy, about 42, is 79. So that was much earlier. So this asks the question whether the Hitchhiker's Guide actually got the idea here from Meissner, Thorne, and Wheeler. I don't know. Anyway, it's an interesting question how you do that in the discrete. So what Regge does is actually quite nice, quite elegant. He kind of considers the triangles in a four-dimensional discrete space as kind of the place where two tensors live. And that's a very modern point of view also. So these are the G and the R, this Regge tensor, and the P, these are two tensors. So these are functions on triangles, should be functions on triangles, like two forms are functions on triangles. And so what he then looks at is, and if that's here, maybe I have here kind of a model. So if you have in 3 dimensions, if you have an edge and you look at all the tetraeder which are attached, what you get is a circular space, right? So that's also in 4 dimensions. If you take a triangle and you look at all the hypertetraeder or chambers which are attached to it, this produces a circular space, right? So that's a circle, and so you can make that very, very concrete in a abstract simplicity complex when you have a simplex. So the boundary is a sphere, and then there is the dual sphere, which is the intersection of the unit spheres of the vertices of that simplex. So for example, if you have a a zero-dimensional simplex in a two-dimensional manifold, and if you have a zero-dimensional simplex in a two-dimensional manifold, the dual sphere is just a unit sphere, the intersection of one unit sphere. If you are in 3 dimensions, then it's the intersection of 2 unit spheres, which is a circle. So you have that dual notion of dual, and what Regge looks at, he looks at the deficit angles of this circular graph. So if it is large, then there's negative curvature. If it's small, there's positive curvature. So you can talk about curvature also there, and that's kind of then the analog of the Regge. And he looks at the analog of Einstein equations, writes down equations, all in terms of angles which you have. I don't like that angle stuff, so for me it's better I like more to think about an abstract, finite, combinatorial object, and then to implement all this kind of geometry or Riemann tensor or whatever, curvature or whatever, in a probabilistic manner. That's also pretty, established in differential geometry. Curvature, you can give us expectations of Gregory-Hopf indices. You can by Croft, and you can look, if you have a length of a curve, take a curve, and then you look at the probability that a random plane hits that curve. That's the Croft, and that's the Buffon needle problem is kind of an example. So you can probabilistically, you can recover the Riemann tensor. This is very nice, especially because of Nash. You can take a Riemann manifold, you can embed it in a high dimensional space, you get the natural probability space. But we actually don't care whether it comes from that. That is just needed, Nash is just needed to justify that you actually get this theory in the limit. So also the Euler curvature, which we have looked at, this week in 136, this Euler curvature, which works for any network, you can actually understand probabilistically. And if you have a network, you embed it in a high dimensional space, you get actually kind of the continuum limit if it approximates a manifold. So this is pretty nice. So there are some nice ideas which come together, and then you can ask yourself what plays the role of this Hilbert-Einstein action. So what Regge suggests is you take the area of the triangle, which is kind of given also as an expectation value of Euler characteristic on that triangle, and then the curvature excess angle, which is probabilistically just the expectation value of, related to the expectation value of the Euler characteristic of the dual of that triangle. So we have a very kind of natural action, and also here when you look at the geodesic, if you look at the, these are kind of one-dimensional parts. Actually this is H1. Here, that was actually wrong. So that's H1. That's the one-dimensional. You look at the one-dimensional part, this gives you length. So this is kind of the length here, and you could just take the length, the expectation of the length. That's kind of more like an action here, which is kind of the square, kind of an energy, not the length. Anyway, what happens is kind of this looks very attractive, simple, and something you can actually implement easily. So you take a finite abstract simplicity complex, and you take a probability measure on functions. You can get all these quantities, and you can see what actually happens, what does maximize this action or minimize this action, and or extremize this action. And it's probably like Regge suggests that the A and B, there's kind of some and actually that's kind of what you have also here, right? So the Regge tensor is proportional to the Riemann tensor. So distances and curvature are here related, and here just also you have kind of also for in one dimensions you have kind of this, you can also kind of see as a relation between quantities like that and quantities like that. I don't yet know whether this works. I just tried to warm up for next week, and I'm excited to cover the classical thing, the classical, Riemann curvature tensor and this Einstein equation next week. And then we also will have a demonstration in class. That's it for today.